So now what happens when the momentum and the force are not perpendicular, or are not parallel, but the force is always perpendicular to the momentum. If the force is perpendicular to the momentum, so let's draw a particle that has some momentum p, the force is perpendicular. The change in the momentum is going to have to be delta p will point in this direction. And that is something which will change the direction of the momentum, but not its magnitude. So if I arrange the force to always be perpendicular to the momentum, the object will not speed up, it won't slow down, but it will continually change the direction that it travels. So let's approach it from the following point of view. You observe an object, we're going to observe a motion and deduce what the force is. So we observe an object. In a time t, it completes a circular track of radius r. So here is the circular track. Let's say it starts there at t is equal to 0. It goes all the way around once. When t is equal to capital T, it comes back to the beginning. There's r. So the t is the period of the motion, units of seconds. If I wait half a period, I wind up right here. T, so the time is equal to half a period right there. T is 1/4 of the period. And I think you can see, so what we want to do is, at any one time, so here is time t, I've got the object, I'm going to put my origin right here. There is the x component of the current position of the object, and there's the y position. So r is a vector with components x of t, y of t, 0. So I'm going to figure out what the position is, and from that figure out what the velocity is, from that figure out what the momentum is, and then use the momentum principle to deduce what the force is that's causing that motion. So I've got, at the time t, I've got this angle theta of t. I don't know what that angle is yet, but I'll find it out. If that angle is theta, there's r is the radius of the circle, so I know this is equal to r times cosine theta of t, r times sine theta of t, and 0, because I'm still not moving anywhere in the z direction. Now theta itself, if I let the time equals, so it's theta when t is equal to pi over 4 should be this right angle there, which is pi over 2. When the time is equal to the period divided by 2, it should be right there. The angle should be equal to pi, and theta when t is equal to the period completely, I should get to 2 pi. I think you see the pattern here. The time, so here it is, period divided by 4 becomes pi divided by 2. Period divided by 2 becomes pi, period becomes 2 pi. The angle we're seeking is equal to, the angle we're seeking is equal to the time divided by the period times 2 pi. So when the period is, so when the time is equal to the period, theta is equal to 2 pi. When we have the period is equal to, when the time is equal to the period divided by 2, we have the angle is equal to pi, and so on. So now this can go into our trajectory, so I now know that r of t is equal to r cosine t times 2 pi divided by the period, r times the sine of t times 2 pi divided by the period, and 0. So that is what the position is. That is what the position is. The momentum is going to have to be a vector that's tangent to the circle, though. So we can find the momentum. The velocity is the time derivative, d by dt of r of t. Another way to write that is r with a little dot on top of it. And these time derivatives, there's a function of time, there's another function of time. What I get is minus r cosine, the derivative of cosine is sine, minus r times the sine t t times 2 pi divided by the period. The derivative of the sine is cosine, so r times Let me do all this right so that I don't make any mistakes. For this one, I get minus r times 2 pi divided by the period times the sine of t times 2 pi divided by the period. That is the correct use of the chain rule. For this one, I get plus cosine, so that's r times 2 pi divided by t times the cosine t times 2 pi divided by the period, and then 0. Notice I've got common factors here of this and this. Now, r times 2 pi divided by t, that is an interesting object. 2 pi r is how far you go. The period is how much time it takes you to do that once. That is the speed with which the object is moving. So I get that the velocity is equal to, I'll factor in r times 2 pi divided by period out from all of those, the speed times minus sine t times 2 pi divided by the period. Let's move this out of the way. Cosine t times 2 pi divided by the period and 0. Here is the magnitude of the velocity vector, and here is its unit vector. The Pythagorean theorem will tell you that the sine squared plus cosine squared of any angle, no matter what that time is, this is some number of radians, this is some number of radians, sine squared plus cosine squared is going to give exactly 1. So that is a unit vector times a magnitude. So now I know what the momentum is. The momentum vector, p, is equal to m times v. Again, we're going to look at the speeds much less than the speed of light, times minus the sine t times 2 pi divided by the period times the cosine t times 2 pi divided by the period and 0. Notice that the momentum is not a constant. It depends on time. Sometimes it's going up at times equal to 0. I've got the sine is equal to 0 and the cosine is equal to 1, so t is equal to 0. The momentum points upwards. And you can see that on the diagram. You're sitting right here, times equal to 0, and you have to be moving upwards. If we let t be the period divided by 2, well, now my unit vector here looks like minus the sine of, well, t divided by 2, it's the sine of pi, times the cosine of pi, and then 0. This one gives 0, this one gives minus 1, and this one gives 0. So now I'm going downwards, and halfway through, I'm right here on the edge of the circle, and I have to be moving downwards. That's p of t divided by 2. So I've got a momentum which is changing in time. Its change in time is caused by a force, dp dt. I calculate this derivative, so I get mv, which is the magnitude of the momentum vector. The derivative of the sine is going to get the cosine, so I get minus 2 pi divided by the period times the cosine of t times 2 pi divided by t. I get the derivative of the cosine is going to give a minus sign, so I get minus, again, 2 pi divided by the period times the sine of t times 2 pi divided by the period and 0. So there is what the change in momentum is. Again, it doesn't look all that simple, but let me factor out this 2 pi divided by t and the minus sign. So I get minus mv 2 pi divided by the period, and what's left inside has got to be, it's dimensionless, it's going to wind up being a unit vector, and it's a special unit vector. We get the minus signs taken care of, so we have the cosine t times 2 pi divided by the period. We have the sine t times 2 pi divided by the period and 0. And I think you'll see this unit vector here, cosine t 2 pi divided by r, sine t 2 pi divided by r, is the same unit vector that's sitting here in the position of the object. I could write this as r times r hat, which is r times cosine t times 2 pi divided by the period sine t times 2 pi divided by the period 0. So that is interesting. This change in momentum points in the minus mv 2 pi divided by the period r hat direction. It has to point towards the center of the circle. So that is an interesting thing, and we can get that from our little analysis of what happens to different dots. So here at the time t minus dt, time t plus dt, there is the momentum before you get to the dot, there's the momentum after you get to the dot. If I write them from the common origin, the initial and the final, I get a change which points back towards the center. So I know the direction that's given by this piece. This is a kind of a nasty way to write the magnitude, though. So the magnitude of dp dt, which is the magnitude of the force that's required here, is equal to mv 2 pi divided by the period, and the 2 pi, if I multiply it by an r and then divide by an r, this thing in the numerator is how far you go away around the circle once in some amount of time t. That thing there, 2 pi r divided by t, is another factor of the velocity. So I get mv squared divided by r. And this is all stuff now that you get from just the properties of the motion. You know how fast it's going and around what circle. And you know what is the mass of the object. So we can deduce, when you see an object moving on the edge of a circle, with a radius r and a velocity v, the force that's needed points inward towards the center of the circle and has a magnitude mv squared divided by r. Now this is not that's the force that's required to make this motion happen. Some people call it the centripetal force, but really it is just the force that's required to make the observed motion. And we'll do some examples in class to clarify exactly how that works.